Good afternoon. Good afternoon, students. Thank you. Unmute your microphones.
Yes, sir.
Good afternoon.
Good afternoon, sir.
Welcome to your favorite hour on Joy Learning SHS. The weather today has not been good. It's been raining all over. So if you have made time to join us for this wonderful journey, I think you have done well. Well, I am George Lokko from St. Mary's, and I'll be leading you on in integrated science. The last time we met on Joy Learning concerning integrated science, we were treating acids, bases, and salt. So we did acids, bases, and salt 1. For the benefit of those of you who were not with us the last time, I'll just recap and then we'll continue from that point. However, if you have any problem, the videos have been uploaded on YouTube. You can revisit it and then watch it. And if you have any question, we'll be giving you an email address to forward your answers and questions there. We said that around us, there are so many chemical substances, and we can classify the substances into several groups based on several criteria. One of the methods we use in doing this is the concept of acids, bases, and salt. So if you look around you, you see you have water, you may have precedent, sometimes you have lemon juice, and then you can also have some medicines, and then you can also have some herbal preparations, which are bitter. Some of them are sweet, others are not. And we said the last time that you can group these compounds into 3 substances, which are sour, which are acids, those which are bitter, we call them bases, and those which are in between, they are neutral, we say they are salts. Now, the last time we defined an acid as a proton donor. So it's a chemical substance that can donate protons. And we also mentioned that protons are simply hydrogen atoms that have lost their electrons. We mentioned several examples of substances which are acidic in our environment. For example, I mentioned the lemon juice. And then also we have a kind of acid that we get from insects. We call it methanoic acid. So those of us who have been bitten or stung by insects before, you will see that when it stings you, the place swells a little. I'm talking about ants, bees, wasps, and the rest. We call that acid methanoic acid. But we also have vinegar, which our mothers or ourselves will be using to clean vegetables and fruits to kill the organisms on them or pathogens before we take them. So there are different types of acids, and we mentioned some of their physical properties. They are sour, they are corrosive when concentrated, means that they can react to surfaces. And then also, acids can change blue litmus papers to red. I hope you learned something about litmus papers from your JHS. So we are going to use some of the things we studied there to continue from this lesson. And then we also went on to say that acids also react with bases to form salt and water. We mentioned different types of acids and some of the things they are used for. So I remember we spoke about hydrochloric acid, we also mentioned nitric acid, and we mentioned what they were used for. Today, we shall continue that lesson. And before we start our lesson, we will have to look at the learning objectives. And by the end of this lesson, I encourage all of you to know how to define acids. We should be able to also define bases and salts and state their properties, like some of the properties I mentioned earlier. Now, after that, you should be able to describe the effect of acid-base indicators. So we're talking about acid-base indicators as well. And then last but not the least, the use of universal indicators and pH scale to determine the pH of a given solution. So like I mentioned in my preamble, we were talking about the uses of some acids. So the last acid left to discuss was sulfuric acid. sulfuric acid. It has a chemical formula H2SO4. So we have H2SO4. Sulfuric acid is very corrosive and it's a mineral acid. This means that it's made from substances dug from the earth crust. But what are some of the uses of sulfuric acid? So on your screen, you will go through together. The first one is that it is used in making paints and dyes. So it means that it's a starting material for industries in the making of paints as well as dyes. And then also, it is used in making detergents such as the washing powder and the shampoos we've been using at home. Sulfuric acid or tetraoxosulfate 6 acid is also used in making fertilizers. Now that we are having problems all over the world, fertilizer is becoming something that is of importance to farmers. And we will need sulfuric acid to prepare or manufacture fertilizers. Now, the cars or the automobiles we see around us depend on batteries. The batteries in them are referred to as accumulators or secondary cells. And one chemical we put in the accumulators or the secondary cell is an acid. And the acid used is sulfuric acid. So again, we say that it is used in accumulators to generate electricity. That serves as a starter for engines. And it is also used in cleaning metal surfaces before coating to prevent rusting. So if you see industry that uses metals, before they use the metal, they'll have to clean the surface and then you can apply the paint, anti-rust, or whichever material they want to do. Now, it is also used as a drying agent for most gases when we prepare them in a lab. So for example, if you are preparing an acid, if you are preparing a gas and the reaction is accompanied by water, and you want to have only the gas, then it means you pass the mixture through sulfuric acid, which will absorb the water moisture from the mixture and allow the gas to proceed to wherever you want to collect it. So it is used also as a drying agent. Now, we have studied something about sulfuric acid as the last example of the acids and its use. Today, we are continuing the story again by looking at method of diluting acids. If you have an acid or you find yourself working in a laboratory and you are presented with an acid, how do you dilute it? So we want to look at method of diluting acids. We said earlier that acids are corrosive, and that means that if it pours on you, it can react with your skin. Some of them can remove all your flesh to the bone, and you'll be surprised the kind of things these chemicals can do. But if you handle them well, you will get the maximum out of it. Industrially, when acids are produced, they are sold at a very high concentration. That means that they have high amounts of particles per given space of the solution or of the acid. So when you buy, you need to dilute it. You cannot use it the way it is given to you. And in diluting it, there's one property about acids. When you add acids to water or you add water to acid, it generates a lot of heat. So there's a high amount of heat associated with it. And that heat energy is what we call the heat of hydration. Hydration meaning you are adding water to the acid. And with chemistry, when you are diluting acids, we always add the acid to water. We don't add the water to the acid. Question, why should we add acid to water and not water to acid? In discussing this, we add acid to water because the acid is denser than the water. So you can note it down. The acid is denser than the water. And we know from the concept of densities that when you have two liquids and you pour one of different densities and pour them together, the denser one will always go to the bottom and the lighter one will always be at the surface. I hope you understand very well. So if the denser one goes to the bottom and the lighter one goes to the top, then it means that in the concept of diluting acids, since the acid is denser than the water, when you add the acid to the water, it begins to go down. Remember, we said it generates heat. So as it begins to settle to the bottom, the heat energy generated will be evenly distributed in the water medium. I hope you follow. So the heat energy generated, which is the heat of hydration, will be evenly distributed. So you will not have it settling at the top. On the other hand, when water is added to the acid, the water is lighter than the acid. So the water stays on top of the acid. And that means that the water-acid barrier creates a lot of energy, and that can shatter or break down the glass. So we always add acid to water and not water to acid, because the acid is denser than the water, and the acid is diluted when it gets to the bottom of the water, dissipating the heat energy evenly. So acids are always added to water to ensure that the heat of hydration is evenly distributed in the acid medium. Students, this brings us to the end of the properties of acids and how to dilute acids. We shall continue the concept by looking at bases. There are so many chemical substances around us, like I mentioned earlier, and some of them, those which are edible, please, not all substances are edible. Those which are edible around us, when tasted, it gives us some bitter taste in our mouth. For example, if you have ever tasted the leaves or the bark, or you have chewed the bark of the neem tree or the neem seed, you see that it is very, very bitter. And we also have some tablets which, when chewed, are equally bitter. Compounds which are bitter to taste are called bases. Compounds which are bitter to taste are called bases. And they occur naturally. You can have them occurring naturally in rocks. You can also have them occurring in fruits. So you notice that some of the fruit substances that we eat, they are quite bitter, but they will tell you that they are very, very important. Now, we also move on to say that bases can also be obtained from parts of plants and animals. You can have bases from parts of plants, like I said, the roots, the stem, and the leaves. All right, the roots, the stems, and the leaves. And we can also have bases, we can get bases also from animals, medicines, and sometimes some of the food substances. I'll pause here and pose my question to you. What is a base? What is a base? Etonam, I'm expecting you to respond to this. Welcome back, students. We had some small technical challenge, but thankfully it has been resolved. We were talking about acids, bases, and salts, and we finished with the uses of acids. The last item we discussed was on the use of sulfuric acid, and we mentioned some of the uses in the making of dye. We also said it is used in making fertilizers. It's used for cleaning metal surfaces. And then we move on to bases, and we said these are bitter substances in our environment, and you can find them in fruits, the plants, talking about the roots, the stem, as well as the leaves. And we also mentioned that you can find them also in foods as well as medicine. In order to help us have standard definition, we said that there are different definitions we can give to a base, but per our syllabus, we are only supposed to learn one. And that one definition falls under what we call the Bronsted and Lowry definition. So we are going to look at the definition based on the Bronsted and Lowry. By definition, we say that a base or bases are substances capable of accepting protons from acid substances. So it means that when you add a proton, which I said is simply a hydrogen atom that has lost its electron to a base can accept it. So we say that bases are, by definition, chemical substances which can accept a proton. So if they ask you to define a base, you can basically write bases are chemical substances which are proton acceptors. They are proton acceptors. All right, they are proton acceptors. Bases are usually oxides and hydroxides of metals, but we can also have bases which are organic in nature. So apart from them being oxides and hydroxides, you can also have them being organic in nature. So we move on to talk about types of bases, just like we did for types of acids, and then look at the types and move further with the story. There are two main types of bases. There are two main types of bases, and these types are inorganic bases and organic bases. So all the bases we find on the face of this can largely be divided into two: inorganic bases and organic bases. So what are inorganic bases? We want to look at inorganic bases. Buried in the earth around us, there are several elements, compounds, molecules, anything you can imagine. We find them in the soil. And when we dig some of them, we can use them to produce useful things. Some of the substances we can get from the earth crust can be used to make acids industrially. And some of them too can be used to make bases. Now, bases that are made from substances that from the earth crust are called inorganic bases. So take note, an inorganic base is a base made from substances dug from the earth crust. It's a base made from substances dug from the earth crust. Okay, so I am listening if you have a question. Is your hand up or you have supported your chin? Mercy. Oh, okay. So it's just that you are listening. I like the attention you are giving to the class. So we said that inorganic bases are bases made from substances that from the earth crust. We call them also mineral bases. So bases that are made from substances we dig from the earth crust are also called mineral bases. And they are usually oxides or hydroxides. So when we say it is an oxide or a hydroxide, then you have the metal chemically bonded to oxygen, or you have the metal or the base or the substance used in making the base chemically bonded to the hydroxide. Let us look at subsources of some inorganic bases. But before we continue, my question goes to Emmanuel Corte. Corte, define a base for us using the Bronsted and Lowry definition.
Please, the base, they ionize in
We can't hear you. Speak up.
solution.
It's like you're having a network problem. Okay. The network is not good.
That ionizes in solution to produce hydro. Okay, sir.
So we say that bases are chemical substances. Is your hand up? Watson, is your hand up?
Yes.
Okay, I want to hear. I want to hear your question. I'm listening to you. Ask your question.
How is ammonia formed?
We will get there. We've not gotten to preparation of gases. When we get to preparation of gases, we will see how ammonia is formed. But to educate a few of us on the platform, ammonia can be formed from what you call ammonium sulfate, all right? Or ammonia, the reaction between ammonium sulfate and a base. So when we learn about bases, then we can add a base to any ammonium sulfate or ammonium salt, and we can produce ammonia. Okay, so when we get to preparation of gases, we'll also go on that exciting story. But for now, ammonia is formed from the reaction between ammonium salt and a base. And you have to heat, the condition is heat. Thank you. I mentioned earlier that this video will be uploaded on YouTube. So even when the class is over, you still have the opportunity to go back and watch, and also share the link with your friends to come online and also watch. We are all learning, and I'm very happy in a weather like this. You are not sleeping by choosing to acquire knowledge. I'm very happy. Now let us move on to sources of some inorganic bases. We look at ammonia, which is a source of a base. It's also one of the bases. Ammonia can be formed naturally by the decomposition of organic matter. So anytime you see an animal that is dead or something that is dead and is decomposing, ammonia is one of the byproducts of the gases which are produced from that decomposition. So naturally, you find it from the decomposition of matter. But like the young man asked earlier, I said in a laboratory, ammonia can be produced by the reaction of ammonium salt with a base and then heating. Now, another example of a source of a base is potassium hydroxide. Potassium hydroxide. This is also a mineral base. We get potassium hydroxide when we burn the parts of plants. All right, so when you burn plants to form ashes, the ashes of the plant, we are looking at plantain or banana peels, the baobab pod, and also cocoa pod. So if you are seeing cocoa pod or baobab, if you dry them and you burn them to ashes, what you get is what we call potassium hydroxide, or locally some people call it potash. And these substances are what we use in making the soap we used to call alatasamuna. I don't know if it is still on the market, but it is one potent soap we used many years ago, and I'm sure we are still using it today. We are still looking at some sources of inorganic bases made from substances that from the earth crust. And on the next item, we have iron 3 oxide. Iron 3 oxide. Iron 3 oxide is obtained from the iron ore. So it means that for you to get the iron 3 oxide, then you can get the iron ore, and that contains the iron 3 oxide. The name of the iron ore is called hematite. Hematite, so you can note it somewhere. Hematite. Aluminium oxide is also a source of an inorganic base, but just like any other metal, you can get them from their ore. And aluminium oxide is obtained from what you call bauxite. Bauxite. So for you to make aluminium, you use bauxite, and bauxite is a source of aluminium, and it is also an example of a base. Calcium oxide, we all know, can be obtained from limestone, but from JHS, we're told that calcium oxide, what some people call cacotre, which is not the appropriate thing, I pray you don't say that again, is obtained from limestone or chalk, ordinary chalk we see around. So we move on to organic bases, but before we move on to organic bases, I'll ask Alice. Alice, are you listening? Give me a source of ammonia. A source of ammonia. Where can we get ammonia? Alice is gone off, so we shall continue. But if Mercy, you can do that for us. Is it Mercy Fufi? Mercy Fufi, give us the source of ammonia. What can we obtain ammonia from naturally? So ammonia, we said, can be obtained from the decomposition of animals and plants. Okay, so we move on to other forms of bases.
What about
we have
from
dopamine, which is a neurotransmitter. Is somebody's hand up?
Yes.
I see a hand up. Please ask your question.
Is ammonia also obtained from urine?
We can't hear you, please.
Is ammonia also obtained from urine?
Oh, the network is not helping, so we can't hear you well. If you could repeat yourself.
If is ammonia also obtained from urine?
Okay, so you can also get ammonia from urine. That is excellent. Okay, so when you go to the urinal and you smell that pungent smelling gas, ammonia can also be obtained from urine. Okay, which school do you attend, please?
I'm an SHS student from Pempe College.
All right, so we move on. It's gone off again. Now, dopamine is also a neurotransmitter and it's also a base. Histamine, these are organic bases. All right, so we have histamine, which is also an organic base, and it occurs in animal tissues. Now, bases, whether organic or inorganic, may be soluble or not soluble in water. So it means that if you have a base and you put it in water, you can have two things occurring. They will either dissolve or they will be sparingly soluble or they will not dissolve at all. Bases which are soluble in water are referred to as alkalis. Alkalis on the screen, alkalis. So soluble bases are what we call alkalis. So let us look at alkalis. So by definition, we say that these are bases which are soluble in water. They are bases which are soluble in water, and they produce hydroxides when dissolved in the water. They produce hydroxides when dissolved in the water. And this means that all bases are alkalis, but not all alkalis are bases. Why did I say that? All bases, all right, are alkalis. All alkalis are bases, but not all bases. All alkalis are bases, but not all bases are alkalis. Let me explain that. All alkalis are bases, but not all bases are alkalis. This is because an alkalis, we said, is a soluble base. But since we have bases which are not soluble, they do not fall under the alkalis domain. So we can say that all alkalis are bases, but not all bases are alkalis. So anytime you are answering a question, particularly the objective option, watch carefully. Sometimes you see statements like this. Let us look at some examples of alkalis as shown in the table below. We have a two-column table with three examples. The first one is called ammonia, which we spoke about earlier. Ammonia, and the chemical formula is NH3. And like Messi said, or was it Fufi who said it, ammonia can easily be smelled in the urinal. That's pungent smelling gas, all right, is ammonia. It's also an alkalis. Sodium hydroxide with the chemical formula capital NaOH is also an alkalis. And potassium hydroxide, which we mentioned earlier that you can get from the ash of cocoa pods and plantain, is also an alkalis. Now that we have a fair idea of what alkalis is, let us look at types of alkalis. Remember, we define a base, and then we said we have two main types of bases. We have the organic and then the inorganic. And then we also went on to say that some bases are soluble in water, others are not soluble in water. Those that are soluble in water are what we call the alkalis. And we just mentioned some three examples not too long ago. However, we want to push the concept further to know whether there are types of alkalis, and if there are, what are they? We have two main types of alkalis. It means that they are all soluble. And we classify them depending on their extent of dissociation or the ability to ionize in water. All right, so we say that there are two main types of alkalis depending on their extent of dissociation or ionization in their aqueous form. In their aqueous form. So it means that when you dissolve them in water, they will dissolve. But how far can they dissociate to give you the hydroxides that you need in solution? Based on this, we have two types of alkalis, those that dissociate completely and those that do not dissociate completely. We want to look at the types of alkalis, and we shall start with the strong alkalis. So we have two types of alkalis. Those that dissociate completely refer to that as strong acids, strong alkalis, and those that do not dissociate completely refer to as the weak alkalis, And remember, these classifications are based on how they dissociate or ionize in solution to release the hydroxide ions. Now, we therefore say that a strong alkalis is simply an alkalis which is soluble in water, but completely dissociates in solution. So it is a soluble base, is an alkalis, and it also dissociates completely in solution. So we say that strong alkalis, they dissociate completely in solution. And examples come in the form of sodium hydroxide. Sodium hydroxide, and on the screen you have the chemical symbol, capital NaOH. And then we also have potassium hydroxide, which is also on the screen as the capital KOH. Now we'll look at their dissociation in water. And looking at their dissociation in water, as shown on the screen, you will observe that the sodium hydroxide in solution, we are looking at the one with the yellow marker. I hope you can see my yellow marker. Now it is a solid here, and you have the water on top of the arrow or the equation line, and it breaks down to give you the pure sodium plus, meaning that it fragments totally into two. So you have sodium plus, which is in the aqueous form, and then you also have the hydroxide, which is a minus and is also in the aqueous form. This is what makes the base a proton acceptor, because it can easily combine with a proton and it will form water. Now we look at the second example here. We have potassium hydroxide. It is a solid. When you dissolve it in water, it dissociates completely. Now, when a substance dissociates completely, we use a single-headed arrow. So you see that we have just one arrow moving from the left to the right. And then you have also, in addition to the water, the potassium ion created and the hydroxide ion created. I hope we understand. So for complete dissociations, we use a full-headed arrow. And then for the partial dissociation, we'll be looking at this. So we say that this dissociation is associated with the release of energy. You also have the dissociation associated with the release of energy. On the screen, it's supposed to be weak alkalis. So please correct it, weak alkalis. And we say that these are alkalis or soluble bases which do not dissociate completely or ionize in water. So it means that weak alkalis are alkalis which do not dissociate completely in water. So we say they are sparingly soluble, Examples of the weak bases which I have cited on the screen are calcium hydroxide. We also call it lime water. So anytime we hear lime water, don't think of any water from a lime fruit or lime juice. It's actually calcium hydroxide. If you're a science student, you know that this is used for testing for the presence of carbon dioxide. We will look at it when we get to preparation of gases. Another example of a weak base is ammonia. So ammonia is also on your screen. The dissociation of these weak alkalis is shown below. So in the case of the calcium hydroxide, you'll notice that it dissociates completely, it dissociates partially to form the calcium 2 plus and 2 hydroxide ions. 2 hydroxide ions, because if you look at the compound carefully, there are 2 hydroxides as a right subscript to the chemical formula. And for this dissociation, we use a double half-headed arrow. In this reaction, the program didn't give us an option, but it's supposed to be a double half-headed arrow. So one arrow points to the right and one points to the left. Okay, then we also have, in the case of ammonia, ammonia also dissociates in water to give us the ammonium ion and the hydroxide. So the ammonia picks the proton from water and generates the hydroxide. And we went on to say that the dissolution is associated with relatively small amount of energy. Because it's a weak alkalis, the energy generated is relatively small. We will look at the physical properties of bases in a jiffy. But before we move on, I want to remind you that this program can be equally shared with friends. So share it with your friends, as many as you like, as many as you have, anybody at all. And if they also want to re-watch the program or they want to learn, they can go on YouTube and then watch it. It's always there. However, if you have a question, or we'll be giving out questions and we'll give you an email to send the answers to. We move on to physical properties of bases. Physical properties of bases. Physical properties, by definition, are properties about a substance that one can use the senses to estimate. So you can see it, you can feel it, and you can also touch it. All right. So I don't know how you see me on your screen, but in my mind, I'm a very fair person. I'm very, very fair. So how you see me is my physical property. I hope you get it. So physical properties are properties one can see, feel, and measure. And just like acids, bases also have their unique physical properties. And some of these properties are, one, they are bitter to taste. Like I said, it is not prudent or wise to put chemicals in your mouth. It's very dangerous. Please don't do that. But anytime you take a fruit or you take a food substance and that food substance is bitter, then we say that it is a base. Now, bases are therefore bitter to taste. They have what you call a soapy or slippery feel. So if you make a solution of it and feel it in between your fingers, they are very, very slippery. That means that they are bases. So any compound or substance you hold that is very, very slippery can easily fall through your hand, if you know you are trying to hold it well, is or contains a base. They are also corrosive when concentrated. So this means that if you pour a base on your skin, it will react to generate salt. If you don't stop it, it will keep reacting until you lose a chunk of your tissue. So please don't go to the chemistry lab uninvited and don't touch chemicals when they have not asked you to do so. Because when you go to the lab, there are rules you have to follow for your own safety. Another physical property about bases is that they change red litmus solution of paper to blue. I hope you remember red litmus papers and solutions when we are JHS. They will give you a litmus paper. Some of them are bluish, all right, and others are reddish. If you put the red one in a base, it turns blue, and if you put the blue one in an acid, it turns red. I hope you remember. So here, it is a property of a base, and we say that bases change red litmus paper or solution to blue. Now, the pH of a base is greater than 7. The pH of a base is greater than 7. What is meant by pH? What is meant by pH? You can send that answer to, please write it, joylearning TV, joylearning TV myjoyonline.com. The question is, what is meant by pH of a solution? So you can send your answer there. Now, bases conduct electricity also in their aqueous or motive forms. So this means that if you have a base and you insert electrodes connected to a power supply, they will conduct electricity. And that means you should be very careful when handling bases and go close to power supplies. I'm talking about electricity. You can be heavily electrocuted. We have on our screen a demonstration, a picture to show that bases are excellent conductors of electricity when connected to power. So in the diagram, we have a bulb, and then the bulb has been plugged into its own socket. And then we also have, as part of the bulb, we have connectors. So we see this rod, all right, this one, and then the other one here, and they are all connected to a power supply. So this is a switch, and then you have a power supply somewhere at the back. So here you have this electrodes inserted into a solution of the base, and it's connected to a bulb. When you turn on the switch or the key and the bulb light, then that means that the base is conducting electricity. And the experiments will show this, and that is why I got this picture for you. Let us look at another example. This is the same diagram of the earlier one we saw. We have a bulb here, and then connected to the bulb, we have a switch, all right, so to regulate the flow of electrons or current, and then we have the switch connected to one of the terminals, and the power supply N2 is connected to another terminal, all dropped in a beaker containing dilute sodium hydroxide. So we have dilute sodium hydroxide serving as the base. So when this switch is turned on, then electricity begins to flow through the circuit and the bulb will light, just like we saw in the earlier example, this example. So we see the bulb lighting in this fashion. So if they ask you to describe an experiment to show that bases are good conductors of electricity, this is the experiment you will need to explain. You only need a bulb, a switch, a wire or conducting wires, and then you need a soluble base connected, poured into a beaker. You can connect the two ends of the connecting wires and drop it in the base. When you turn the switch on, the bulb will light, showing that the base is a conductor of electricity in the aqueous form. So we look at another property of bases. This young woman here drank something and the thing looks very bitter. So here it's possible that the person took cocoa that is very, very bitter. We have the bitter ones. I'm sure you've taken some before. And when you take something that is bitter, you don't have to say it. Your facial expression will show that what you have taken is not palatable or it's not nice. So our young lady here tries something like that, and it shows that bases are bitter.
Please, sir.
We mentioned also that bases are slippery to feel, or they have a soapy feel. We are
What's
showing you
the
this picture
difference
so
between
that in the event that you are writing and you forgot it, you can quickly remember. Is somebody saying something? Hello?
please? What's the difference between sour and bitter?
So somebody is asking, what is the difference between sour and bitter? This is an interesting question. When we say a substance is sour and when we say a substance is bitter, sour substances have this biting characteristics on the gum. So it is a substance that has this biting. It's like it's reacting with the gum and it makes the gum or the mouth very dry. Now, bitter substances are detected naturally on the tongue, but sour substances affect both the tongue and the oral part of the mouth, every part of the mouth. So I hope we are clear on that. So we say a substance is sour when you can detect it in every portion of the mouth and also on the tongue. But for bitter substances, we detect them at the back of the tongue. I hope you understand. All right. So we said earlier that bases have this soapy feel, and we have this picture to demonstrate. So anytime you use soap to wash your hand, you will notice that it is slippery, and that means that it is basic or it contains a base. One property about bases that we mentioned was that they are corrosive when concentrated. So don't pour it on your hand and don't also pour it on surfaces. They will destroy or react to the surface, maybe spoiling the aesthetic features of that substance. Let us look at our favorite litmus test. In this diagram, we have two solutions contained in two different beakers. We have an acid, and then we also have a base. Now, on our left-hand side on the screen, A litmus paper, which is blue in color, has been dipped into an acid solution. And you notice that the portion that is in touch or in contact with the solution has turned red. And that means that chemical substances which are acidic will always change blue litmus papers to red. Now, on the right-hand side, there is a greenish solution which we don't know its identity, whether it is a base, an acid, or even a salt. A red litmus paper was dipped into it, and you'll notice that the part of the solution that is in contact with the litmus paper has changed to blue. And one physical property about bases is that they change red litmus paper to blue. We also have on our screen another diagram. And with this diagram, we have an acidic solution starting from the left. We have a basic solution, and then we also have a basic solution, and we are using litmus papers and a universal pH paper. All right, we have what we call the universal indicator, which is either in the solution form or in the paper form. If you look at the diagram on the left, I'm talking about this one. A blue litmus paper was just dipped into an unknown solution, and the portion in contact with the solution has now become red, meaning that this substance here is acidic. Again, if you check the next example, it is greenish in nature. A litmus paper has been dipped into it. The portion of the litmus paper in touch with the solution has become blue. That means that the solution is basic. The solution is basic. And the last example we have here, we have a universal pH paper. A universal pH paper, it is used to determine different pHs. So even though it is an indicator, it can tell you whether it is a strong one, a weak one, based on the pH. We'll look at the pH. Remember, I gave you the email to send your answer to. We'll look at that answer when we get there. So when you dip a universal pH paper into a solution of a salt, it changes to blue. But not just the blue. This one tells you that so far as it is blue, the solution is basic. But to what extent is this solution basic? So you match the color of this paper, the color you have now on the paper, on the color chart. This is what we call the color chart. If the color falls within the red to the orange zone, then it is acidic. If it falls to the light green to the one above the, which is purple, deep purple, then it is basic. If it's somewhere neutral, it is greenish. So for the paper we have here, when you match, you see that the solution, even though it's bluish, will have a pH of about 12. And that means that it's a very, very strong base, a very, very strong base. Why did I bring you this picture? In your integrated science test of practicals, the chemistry option, a diagram of this sort can be given to you, and then they'll indicate the various colors on the litmus paper, and they'll ask you to use the colors to identify the content of the beaker. So if they put a litmus paper in the solution and the litmus paper turns red, then the solution there should be acidic. I hope you get it. And if you put a litmus paper in a solution and it turns blue, then that solution is basic. Sometimes you can be given a solution or solutions, and they'll give you their various pHs, and they'll ask you to classify them into strong, weak, or neutral solution, weak acids or neutral solution. When we get to the pH column, we shall look at this wonderful concept. So we are still on bases and the physical properties of bases. Another example that can be presented to you during a test of integrated science chemistry option practical test is where you'll be given a solution, an unknown solution. They'll give you any color solution, or even a gray solution. And you have two litmus papers dipped into it like we have here. Now for this solution, if it is not known, and after dipping the two litmus papers, one was red, like we have on the left, and the other one was blue, just after dipping them into it, we realize that the one with the reddish color, a portion of it has turned blue, and the blue still remain blue. Now, if you have a solution which keeps the base, the litmus paper blue, even though the litmus paper is blue, it could be that the base is, that solution is neutral, or it is neutral to litmus. But if you dip into that same solution a red litmus paper and it changes to blue, then that solution is now said to be a basic solution. I hope you are following. So you can be given a test of integrated science question where you use 2 litmus papers to identify the content of that solution. Now, if it is an acid, then we expect the opposite. So if you have the red and you dip it into the red, nothing happens to the red litmus paper. But if you dip the blue in there, the blue will change to red, indicating that you have an acidic solution. Now, solutions which are neutral wouldn't have any effect, all right, on the litmus paper. So you see that even though we dip in red and we also dip in blue, at the end of the process, they retain their colors. Let us look at the chemical properties of bases. Chemical properties of bases. A chemical property of a substance is simply a property about a substance that can be verified using only chemical reactions. So we say that a chemical property of a substance is simply a property about that substance that can be verified using only chemical reaction. Remember earlier I said my physical property, one of my physical properties is that I am fair, and you are assessing my complexion based on your size. But with the chemical properties, we don't use feelings. We subject the substance to chemical reactions. So in the human terms, you can't just look at somebody and say that this person is a thief or is spiritual. You can't use your eye, but here you are using your senses. It goes beyond that. So to verify that part for the base, we use chemical reaction. One of them is that bases react with acids to form salt and water. Bases, they react with acids to form salt and water. So we have on our screen a simple projection of an acid, which is HCl, and the base we are interested in is the Alkalis sodium hydroxide. Remember, it is a strong base. It will dissociate completely in water, as said earlier, and that is going to form the salt, which is sodium chloride and water. The salt, which is sodium chloride and water. I cited another example again. This is a weak alkalis. If you remember, weak alkalis do not dissociate completely in solution, or they do not ionize completely in solution or in their aqueous form. So if you react this alkalis with this acid, it's supposed to give you the calcium nitrate, not this one, the calcium nitrate. So you have Ca into bracket NO3 bracket close 2. So you have something like this, Ca the bracket NO3, and you have the 2 out there and not the chloride there. So in addition to that, you also get your water. So one property about bases is that they react with acids to form salt and water. They react with bases, acids to form salt and water. This program will still be beaming live on YouTube. So you can share, you can watch anytime. If you don't understand, giving you also a site, you can send your question there. It will be answered for you. So we move on to the next property about bases. We can say that bases react with ammonium salt. So the person asked the earlier question is being addressed here now. Bases react with ammonium salt to produce ammonia gas. So we say that bases react to liberate, all right? They react to liberate, to liberate ammonia gas when heated with ammonium salt. Ammonium salt, this one. So when they are heated with the ammonium salt, then ammonia is produced. The gas is identified by its urine-like characteristics. So the one who said that you find it in the urine now, see, you are now correct. It has this urine-like smell, this pungent, strong, excruciating smell. So that when you go to, I'm sure at school, those of us in a public school, sometimes when the place is not clean, particularly in the afternoon, it is very, very pungent, and it's because the sun is hot, more ammonia is produced. So we have on our screen an ammonium salt. Here we have ammonium sulfate, or better still, ammonium tetraoxosulfate 6, which is an ammonium salt, and it is reacted with calcium hydroxide, and we heat the system. Remember, heat is necessary for this. So when we heat you form the calcium sulfate and ammonia in addition to water. My question goes to Emmanuel Corti. If you are producing ammonia using this method, it means that you can have water produced, right? Good.
Yes, sir.
Now, if the water produced wants to be eliminated from such a system, I mentioned one compound earlier, which we can use to absorb water. What compound is that? Which compound is used for absorbing water in gases?
Sir, ammonium.
So when I was treating the acids, I mentioned that there is an acid that can be used as a drying agent. It is not appropriate for this, but which acid is that?
Sir, sulfuric acid.
So we use the sulfuric acid. Sulfuric acid can be used to absorb water. But for this reaction, what I want to tell you here is that we cannot use sulfuric acid to absorb the water here because sulfuric acid too can react with the ammonia. So if you are preparing ammonia in the lab, we don't use sulfuric acid as a drying agent. Even though it is a drying agent, we don't use sulfuric acid because it's an acid and this is also a base. So it will react to give you the salt again. So you will not get anything. There are other compounds we can use to dry this ammonia. We will talk about it when we get into preparation of gases. Another example we have on our screen here is ammonium nitrate. Ammonium nitrate or ammonium trioxynitrate 5. Ammonium nitrate. We find this in fertilizers. Ammonium nitrate. When you heat ammonium nitrate with calcium hydroxide, you form the calcium nitrate, which is a solid, and then you have ammonia again produced, which is a chemical property of bases. So when you heat a base, so this is a base here, when you heat a base with an ammonium salt, it generates ammonia. So far, we have mentioned two properties. Bases react with acids to form salt and water. They also react with, they react with ammonium salt when heated to produce ammonia. Let us look at this setup carefully. We are young students. We found ourselves in the lab. Our chemistry teacher has tasked us to prepare ammonia and test for it. How do we do it? Using the basic concept of acids and bases that we have learned so far. We said that acids can react with bases to form salt and water. And another property about bases is that they can produce ammonia gas when heated with bases. All right? Now, for us to do this simple test, we will need a test tube on your screen. This is a test tube. And then you also need a test tube stopper. So we have a stopper with one hole drilled in it. And then you also need what you call the delivery tube. We'll go into detail when we are preparing ammonia gases itself. So we have this setup. So we have the ammonium chloride here at the back of the glass, and then we heat it with fire from the Bunsen burner. So this is the Bunsen burner. As you apply the heat, the ammonia reacts with the base you have mixed with the ammonium salt. The base reacts with the ammonium salt you have placed in there, and the ammonia gas begins to come out. For a test like this, usually we slant the test tube upward so that the water formed in the process will not interact with or interfere with what we have here. So usually we slant it downwards. So the test tube is supposed to look like this, so that the water form will rather be somewhere here and it will not be where you have the heating process occurring. Why should we do that? We do this in order to prevent cracking of the glass. Cracking of the glass. So sometimes if they ask you, those of you doing electric chemistry, they ask you why we should slant the test tube or the boiling tube or whichever equipment we are using when preparing ammonia, is to prevent the water from interfering with the reaction, which will result in a cracking of the glass because the glass doesn't expand and contract uniformly. Now the gas we have produced will go through this delivery tube and then ascend outside. So if you want to test for it, you just bring your red litmus paper here, but you shouldn't just use a dry red litmus paper. You should use a damp red litmus paper. it should have some amount of water in it or moisture in it, and then it will change color to your favorite blue. So if you want to talk about the chemical properties of bases, one, we said it reacts or they react with acids to form salt and water. And then two, bases also react with ammonium salt when heated to produce ammonia. If they ask you to draw a simple diagram, you can sketch this line diagram for them and you score your points. All too soon, we are getting to the end of our lesson. But this lesson cannot be ended without a very simple assignment. Write these questions down. Write the questions down. Question number 1. State 4 types of acids. State 4 types of acids. State 4 types of acids and their sources. State 4 types of acids and their sources. Question 2. Distinguish between organic and inorganic acids. Distinguish between organic and inorganic acids. Distinguish between organic and inorganic acids. And then question 3. State 3 physical and chemical properties of acids. State 3 physical and chemical properties of acids. State 3 physical and chemical properties of acids. You will notice that this assignment is on acids because we completed acids today. But since we are also done with bases, repeat the same questions for bases. So it will read, state 4 types of bases and their sources. Distinguish between organic and inorganic bases. Then state 3 physical and chemical properties of bases. So soon, our time is up. We have exhausted our class. I've enjoyed your class and we are about to end, but we cannot end without you asking questions. So I am waiting to hear your questions, then we can all wrap up. Please don't ask me the questions I gave you. Those ones are for you. Go and do them. And when we meet the next time, I'll also review it and we'll discuss them. Well, no question has come up. Nobody has raised their hand. So soon, our time is up. And today we learned about the properties of bases. We recapped the remaining parts of the acids and we learned about bases. We said that bases are proton acceptors and went on to talk about examples of bases. And we said that we can get bases from ammonia, decomposing substances, or we can get them from the earth crust in the form of potash or by burning substances. And we have different other ones which are also organic, like the histamine, like the dopamine, like we mentioned. From there, we spoke about the properties of bases. We mentioned that they have physical properties and chemical properties. We ended the lesson with the chemical properties, and we said that bases react with acids to form salt and water. And the last one is that bases react with ammonium salt when heated to generate ammonia. All too soon, our time is up. You are supposed to send your answers again. I'll repeat, please take your papers and write them if you don't have them to Joy Learning TV. The answers are supposed to go to Joy Learning TV at myjoyonline.com. Joy Learning TV at myjoyonline.com. I am George Lokko. They call me Sir Lokko from St. Mary's. Enjoy the rest of your Saturday. Thank you.